Swayam Prabha. Digital India. Educated India.
So, we will continue from where we left off in the last class. What we did in the last class was derive the transport equation for vorticity, okay. And I am just going to write this equation again, and the equation which I had for vorticity was this. By dy equals nu times del squared omega. This is the equation we derived for vorticity. What I want to show is that this equation is very similar to your momentum x momentum equation, okay. If you look at the x momentum equation, you have du by dt plus u du by dx plus v du by dy equals minus dp by dx plus mu del square u, and I will put a row here, okay, plus rho gx. So, I wanted you to understand that here what we do is we are talking about this term is the accumulation of the x momentum. This is the flux of momentum because of convection. This is the flux of momentum because of diffusion, okay. So, I just want you to look at both of these. Instead of u, I have just put omega here. This is the one which is getting transported. So, d omega by dt, this u is replaced by omega, and this u is again replaced by omega. So, this is diffusive transport of vorticity, convective transport of vorticity, and accumulation of vorticity, okay. So, this is basically your vorticity transport. So, this is diffusive, these two terms are convective, okay. And what we can do is we recognize that omega is minus del square psi. We derived this in the last class, okay. The vorticity can be written in terms of the stream function, and once I do that, I can write this in two ways. I am just going to replace the u and the v in terms of the stream function, okay, which we have done before. So, d omega by dt plus u is d psi by dy d omega by dx plus, or rather v will be minus now, minus d psi by dx d omega by dy equals nu del squared omega. What have I done? I have replaced the u and the v, the velocity components, in terms of the stream functions, okay. So, basically how did I derive this equation? I started with the momentum equations and I eliminated pressure by doing a cross differentiation. X momentum equation I differentiated with respect to y momentum equation I differentiated with respect to x, subtracted, and I got this equation, okay. It is just simple manipulation, and now pressure is eliminated, and these two equations have to be solved simultaneously. These are coupled equations. This is a relationship between omega and psi, and this is also a relationship between omega and psi. Okay. So, this is so these two equations are solved together. Okay. Yeah. So, the moral of the story is, in the stream function vorticity formulation, we solve these two equations, find the stream function. Once I find the stream function, I can find the velocity. Once I find the velocity, I can substitute it back in the momentum equation and find the pressure. Okay. So, I do not have, I mean, I can do this numerically, for example. So, one thing which I want you to recognize is that these terms are the nonlinear terms, these two terms. These two terms here are the nonlinear terms, and because they are the nonlinear terms, when you have to solve, why is it nonlinear? Because the two dependent variables psi and omega, they are multiplying each other. Okay. If these terms vanish, they are not around, then the equation becomes linear. So, the source of the nonlinearity which causes the numerical problem when you are solving these equations, because of which you have to solve things numerically, are these two terms. Okay. And nonlinear terms, hence the nonlinear terms require a numerical solution. Okay. So, now what I want to do is, I want to talk a little bit about dimensionless analysis that we briefly did earlier for one of the problems, and explain a couple of things. So, under what conditions is it possible for us to neglect these nonlinear terms, and these nonlinear terms come from this u du dx v du dy. If you look at the derivation, the nonlinear terms come from the left hand side. Okay. Again, this is the nonlinear term, because u is multiplying the derivative, v multiplies the derivative. So, these are the nonlinear terms that are causing the problem. Okay. So, under what conditions, or before, under what conditions can we neglect the nonlinearity? Okay. Before I proceed further, you might see in some books, for example, this particular vorticity transport equation written in a different form. Okay. For example, this may be written as d omega by dt, another representation of let us say equation 3, although I not put 1 and 2, I am just going to call this equation 3. Okay. And this is let us say 2, and this is 1. D omega by dt remains as it is, plus d by d So, you might see some books have this kind of an expression. So, what is this term? What is this term? This is basically the Jacobian of a matrix. Okay. This term is nothing but d psi by dx, d psi by dy, d omega by dx, d omega by dy. You take the determinant of this. The determinant of this is d psi by dx multiplied by d omega by dy minus d psi by dy times d omega by dx. Okay, that is exactly what I have here. D psi by dy, what did I do? Maybe it's a plus sign here, huh? So d psi omega xy d psi by dx. So this is a short form notation for this the determinant of this matrix. So let me make sure the sign is right. D psi by dx, d psi by dy, d omega by dx. This, so this d psi by dx multiplied by d omega by dy minus this, okay, and therefore there won't be any plus sign. This will be a plus sign, okay. So that's what we have. What I'm trying to tell you is, I mean, I'm just trying to make you comfortable with different notations which people may use, so you shan't get overworked about it, okay. Anyway, now the question is, how do I neglect this term, or under what conditions can I neglect that term? For that we go and do dimensionless analysis. Yeah, is there a minus sign? Where? Here? You think so? I was not sure. Is there a minus sign here? Oh, yeah. I need to take the minus out and then get it. Correct. Thank you. Yeah, I was thinking whether it's minus or plus. Sometimes people write it the other way. Anyway, you know how to do this now. This is right. This is a minus sign. If you write it omega first and psi later, then you will get plus sign. Okay. Yeah. Thank you. I want to talk about under what conditions we can neglect the nonlinear terms, and for this we go to dimensionless analysis, the scaling. Okay, we go to dimensionless analysis to understand when the nonlinearity can be neglected. Okay. So now let's look at the Navier-Stokes equations. And just to keep life simple, I am just doing the scalar version, okay, plus rho g gx. Now what we can do is we can combine the pressure term and the gravitational term, okay, into one term and call it a modified pressure term. For example, if I define this as minus dpm by dx plus mu del square u. What is minus dpm by dx equals minus dp by dx plus rho gx. Okay. What have I done? I am combining minus dp by dx and rho gx into one term here, minus dpm by dx, and this can be written as minus d by dx of p minus rho gx x. Is this clear? So rho is a constant, the gravitational acceleration in the x direction is a constant, okay. And if I differentiate this thing with respect to x, I will get plus rho gx. So, this is equal to this. So, Pm is nothing but P minus rho gx. So, Pm is a modified pressure which is P minus rho gx x. All I have done is combined the pressure term with the gravity term and take out the minus sign out, minus, because this derivative with respect to x, I have added an x there, okay. This is like a hydrostatic pressure which I am trying to subtract, and this is my modified pressure. So, I am going to use this equation. So, point is, in most of our problems I can do this, combine and talk in terms of work in terms of this modified pressure. Only if I have some free surface flows, then this kind of an approximation can be done, because the surface itself is changing, okay. But normal, and that is something which civil engineers who are worried about waves, they are worried about it, in which case one Froude number will come, one additional Froude number comes. So, anyway, for our today's purpose, we do not need to worry about it. I am going to make this equation dimensionless, and I am going to start, this is a dimensionless variable which is u divided by some u characteristic, okay. So, star represents dimensionless variables, okay. And t and x characteristic, y characteristic, I am choosing as some L, some length scale L, depending upon the problem. So, basically I am going to choose the same characteristic scale for u and v, and v star is defined as v divided by u characteristic, okay, and x star is x divided by L, y star is y divided by L. I am just going to go through this in a bit of a detail, then you can do it everything else on your own. And that is all I have. And now I need to choose my pressure characteristic. So, P characteristic I choose as mu times u by L, okay. You can check that this has units of pressure. So, all the star variables do not have dimensions, the characteristics have the same dimension as the variable. So, this has units of velocity, this velocity becomes dimensionless, okay. So, now I am going to substitute then the other independent variable is t characteristic, okay, the time, what I have to make time also dimensionless. Since I have made, this is my length scale L and this is my velocity scale UCH, t characteristic will be L divided by u characteristic. This has units of time. This is one possible choice, okay. So, t star will be t divided by t characteristic. So, I am going to look at the first term here, du by dt. I am going to write this as everything in terms of the star variables, okay. So, u is nothing but u star multiplied by u characteristic, okay. This is therefore d u characteristic multiplied by d u star divided by d t characteristic t star. Clearly, the characteristics are all constants, okay. So, I can pull it out of my derivative and I get this is u characteristic times du star by dt star by t characteristic L by u. So, this is u characteristic squared by L times du star by dt star. We need to convert everything to star variables now. So, what about u du by dx? this is going to be written as u characteristic times u star times d by d x star times x characteristic times u characteristic times u star. So, u I am writing as u characteristic multiplied by u star everywhere, okay, and this is, so this can be written as u characteristic squared divided by L multiplied by du star by dx star multiplied by u star. Similarly, v du by dy can be written as u characteristic v star times du characteristic u star by d y characteristic and x characteristic are the same, u characteristic square by L star, okay. And then I have the other option, which is what is this, mu del square u, that is going to be written as, okay, this will have two, this is d square by dx squared, d square by dy squared is there, and x and y have the same length scales, okay. So, I am going to write this as x square. So, this can be in terms of star variables, I will get u characteristic divided by L squared times del square by del x star squared plus del square by del y star squared times u star, okay. So, L square comes out here, great, and the pressure modified will be P characteristic by L. When I convert this to star, I will get P characteristic in the numerator. When I convert the derivative to dimensionless, I will get L in the denominator, okay. That is what I am writing here, is equal to d by dx star of Pm star. This is basically in x direction, so del Pm is dP by dx. We substitute all of this in the equation. What do you get? Rho times du by dt was u characteristic squared by L, that comes out common everywhere, okay, the way I have chosen my scales, plus to P characteristic, I said I am going to choose as, I wrote it, mu u by L. So, I am going to write this as minus mu u by L times dPm star by dx star, and there will be L squared here, because one x comes out, one L comes out, okay, plus mu times mu by L squared of times u characteristic times del star squared u star, okay. So, because del square has been converted to del star, the L square comes at the bottom, this guy gives you a u characteristic, fine. So, now I can just divide everywhere by mu times u pressure and u characteristic, okay. So, I divide everywhere by this thing, divide by mu times u characteristic by L squared, the whole equation. Then what do I get? Rho's UCH times L by mu, okay, because I am just dividing this term by this, I will get that times du star by dt star star, this is a star, huh? I am forgetting to put the stars. Okay. So, this term here is what is your Reynolds number, and what I am trying to tell you here is that in the limit of low Reynolds number, when Re is very, very small, I mean again we are assuming that this term and this term are all comparable, okay, the way I made my equations dimensionless. These terms are, this is of order 1, this is of order 1, and all these terms are of order 1, okay. This is basically what we have to ensure when we make our equations dimensionless. Only then, if they are of the same order, then if I multiply this by Reynolds number, the value of the Reynolds number tells you what is the importance of this force or this term. If the Reynolds number is very, very low, I can now neglect it. Suppose Reynolds number is 10 power minus 5, then this term on the left hand side is negligible, okay. So, for if Re is very much less than 1, LHS can be set to 0, okay, and this particular thing, and remember Re is the ratio of inertial forces to viscous forces. So, basically this means inertial terms are negligible. When I say Re is low, that means the inertial terms are negligible, inertial forces are negligible. And if you remember your fluid mechanics, Reynolds number is the ratio of inertial to viscous forces, okay. What I am trying to tell you here is that this term is the Reynolds number, okay, which represents the magnitude of inertial forces to viscous forces, and these terms which are with the stars, they all have the same order of magnitude. So, then only then I can say for low Reynolds number I can neglect this. So, when you make things dimensionless, you have to make sure that these terms are all of the same order of magnitude. That is the whole idea. Only then, especially if I am not making any approximation, then it does not matter. But now I want to make an approximation. I want to ask, when can I neglect this? I can neglect this for low Reynolds number, okay, low inertial forces, and what that means is, I mean, this is called the creeping flow limit or the Stokes regime, okay. So, for low Reynolds number, I can neglect the nonlinear terms can be neglected, and I have basically a linear equation, okay. So, when it comes to the low Reynolds number regime, so for low Reynolds number, we can say 0 equals minus gradient of P m star plus del star squared u star, okay. And so, clearly this is your creeping flow limit. Now, the nonlinear terms have disappeared, and there are again 4 variables. You have to write this for all the 3 directions, 3 velocity components, and there is pressure. You need one more equation, which is the continuity equation, and that is del star star dot u star equal to 0. This is your continuity. Okay. So, now I want to go back to that equation in terms of vorticity and the stream function, okay, and going back to the vorticity and the stream function equation, I get del square psi equals minus omega, and we wrote for low Reynolds number, all the terms on the left hand side could be neglected because they are the terms that are coming from the inertial terms. Okay. So, basically d omega by dt plus u d omega by dx plus v d omega by dy can be neglected, and what you have is del square omega equals 0. Okay. So, that was this is the from the vorticity transport equation. The non-linear terms, remember, are coming from these terms here. That is what gave you the d omega by dt. So, these terms, when limit of low Reynolds number, I can neglect it. Okay. And then in the limit of low Reynolds number, I have only these two equations to solve. For low Re, I get del square psi equals minus omega and del square omega equals 0. Okay. Or what I can do is I can operate on both sides by del squared, and what will I get? Del square of del squared psi equals minus del squared omega, which is 0. Basically, I have a fourth order equation in psi. Okay. I want you to remember that what I have done is only for Cartesian coordinates. When I go to cylindrical and spherical, this del square gets modified to e squared, another operator. Okay. So, this is true for Cartesian coordinates, okay, and 2D flows. So, what we have done is, if you do not want to solve two equations and two unknowns psi and omega, we can eliminate omega like I have done, but I can do this in the limit of low Reynolds number, and I get a linear equation, and this is called the biharmonic equation. Of course, you can eliminate write this in terms of psi also. I get two equations are coupled. Okay. But I mean, we do not want to solve two equations, we want to solve only one variable, suppose only psi, then this is what you get, and it is a linear. I mean, so I made two things, converted everything in terms of psi. I have also said Reynolds number is low, so I get this linear equation. Okay. Now, with the linear equation, you can think in terms of solving using methods like separation of variables, trying to get an analytical solution. Okay. That is the whole idea. The other point is, because it is a fourth order equation, I need 4 boundary condition each in x and y. So, now I want to just illustrate the boundary conditions from what we did earlier. So, take this problem of what are the boundary conditions. Okay. I am going to illustrate this with this problem of the lid driven cavity. Okay. U is equal to u naught at the top surface, and let us say this is x equal to 0, x equals 1, y equals 0, y equals 1. So, now the no penetration condition tells you the at x equal to 1, the no penetration. What is the meaning of no this is x equal to 1 boundary? No penetration means the x component of velocity is 0. Okay. That is u is 0, which means in terms of stream function d psi by dy is 0. No slip is the tangential component of velocity is 0, implies the tangential component is 0, which means d psi by dx is 0. Okay. So, now basically what this means is if d psi by dy is 0, because x is constant, along this psi is not varying, and I can choose my psi to be some reference value, I can choose it to be constant or 0. So, this implies psi equals constant d psi by dy equals 0 implies psi equals constant at x equals 1. Along this psi is not changing, psi is constant here, okay, and I say the perpendicular. So, these are two conditions I am getting. Similarly, I will get two conditions everywhere, okay. So, basically what I am saying is this will correspond to one streamline. So, psi equals constant, which I am taking as 0, and d psi by dx is 0. Here psi equals 0, psi is constant, along this again using the same argument, and you will get d psi by dy is 0. Here you will get psi equals 0, d psi by dx equals 0. Here x component of velocity is d psi by dy. Here you will get d psi by dy is equal to u naught and psi equal to constant. It is going to be the same constant everywhere, because there will be one streamline hugging this whole thing, hugging the boundary. When I am physically, you think about it, I have one stream, this liquid is moving, is going to drag the plate is moving, is going to drag the liquid. This one liquid layer is going to be hugging the walls, okay. So, there is going to be one streamline. Now, on the streamline psi is constant, I am taking that constant as 0 as a reference case, okay, because stream functions are determined to only within an arbitrary constant. So, this is constant, and everything else, the normal, and everywhere else the normal derivative is 0, d psi dx, d psi dy, d psi dx, and here d psi dy is non-zero, it is u naught, the plate. So, this non-homogeneity is the one which is driving the flow, okay, and you have enough boundary conditions now. Basically what we have done is we have converted the boundary conditions on u and v to boundary conditions on psi, okay. All the boundary conditions which were there on u and v is converted to boundary conditions on the stream function, and you have enough boundary conditions you can solve, okay. That is the point I am trying to make here. The other, you can argue any which way, psi is constant here, psi is constant here, at this point psi has to be the same, so psi has to be same everywhere. You can argue any way you want. So, you could now, because these equations are linear, try to do your solutions using some analytical approach, otherwise you have to use a numerical approach, okay. So, that is the key thing. The other thing I want to do is just discuss one more scaling which people use, okay. What if P characteristic is rho u squared, u characteristic squared? What happens if you choose your P characteristic as rho u squared, not what we did earlier, mu u by L, okay. I mean you have a choice, okay. So, I want to just discuss what happens, because you should know that, like I told you, it is not easy to decide what the characteristic scales are in a problem, okay. So, supposing we do this, I am just going to write this and take a shortcut, because I am not going to explain this in detail now. This is a dimensional equation, and I am going to make it dimensionless, and like we did before, okay. So, I will get rho u characteristic squared by L times dy star equals minus rho u characteristic squared by L, because this is going to come out as rho u characteristics, okay, squared. That is my scale. Okay, del star squared u star. So I have just done the same thing, converted all like we did before. I am converting all the variables without the star to the variables with the star. Okay. Now what do I get? I am going to divide by mu u characteristic by L squared like before. I divide by mu u characteristic by L squared. Okay. What is this? This is this coefficient. And what do I get at the end of the day? I will get a Reynolds number multiplied by the du star by dt star plus u star du star by dx star plus v star du star by dy star equals, again I will get Reynolds number here. Okay. So if I do the scaling using this variable for the p characteristic, I get a Reynolds number here as well as a Reynolds number multiplying my pressure gradient in the dimensionless form. Okay. Now if I were to set my Reynolds number 0, go to the creeping flow limit. If I go to the creeping flow limit, what will happen? At Reynolds number very much less than 1, we will get del star squared u star equal to 0. This is just the momentum, because I mean assuming all the scaling has been done properly, I will neglect this term and this term, I get that. And in addition to that, I have continuity equation. So is this, do you see a problem which arises here? There is a problem because this is a system of 3 equations, one in each direction, x, y and z. This is a continuity, so I have totally 4 equations, okay, but only 3 variables u, x, uy, uz, 3 velocity components. So I am saying I have 4 equations, 3 velocity components, and so we have a problem. Okay. So basically what this means is, in the earlier scaling I had 4 equations, 4 variables after making the creeping flow approximation, pressure and the 3 velocity components. But here what has happened is, by this new scaling that I have done, so something wrong with the scaling, I can't use the scaling. Okay. So this is how you have to think about how to go about making the scales, choosing the scales when you are analyzing a problem. Okay. You have to do different combinations and see which is the one which makes sense. In the earlier scaling, what we did was we said pressure forces and viscous forces are balancing. Okay. Here what we have done in this new scaling, the viscous forces are equal to 0 is what you are getting, nothing to balance the viscous force, nothing to drive the flow. So you got to think of the problem both mathematically and physically when it comes to doing dimensionless analysis. Okay. So what I am saying is, in the limit of Reynolds number low, we can, our equations become linear. Okay. If the Reynolds number is not low, then you have the non-linear terms, you have to solve things numerically. So because the equations are linear, I can do analytical solutions, number 1. Number 2, when it comes to scaling, you have some choice of scales, and the only way you can decide what is the right scale is by going through the exercise for different scales and figuring out, when you are making this approximation, do the approximate equations that you finally get make sense. In this case it does not make sense because the pressure term vanishes, inertial term vanishes, only viscous terms remain. I have this problem of 4 equations, 3 unknowns, I can't solve. Okay. So, just think about it. Thank you.